So hello everyone, today we'll be discussing about static range queries. So it basically has two techniques. One is the prefix array. Okay, let me type it. Yeah, one technique is prefix array. The other technique would be sparse tables. So when to use each one of them? Okay, prefix array basically works on the stuff like let's say you want to find something like some product or something like that. These operations are associative and invertible, isn't it? Like sum is associative and invertible, like inverse of sum is subtraction, and also product inverse exists, division is the inverse, and it's also associative, isn't it? But let's say you want to find out something like a minimum or a maximum, or let's say you want to, okay, basically the opposite, which is non-invertible, like inverse doesn't exist and it's not associative. Okay, it's not associative. In this case we use something known as a sparse table. So let us see the first question in CS problem set related to range sum query. Given an array of n integers, your task is to process q queries of the form what is the sum of values in range a to b. Okay, so tell me what's the operation which we are asked to do? Sum, right? Sum. We already discussed sum is associative and invertible. So which data structure should you go with? You should go with a prefix array. You should go with a prefix array. How does a prefix array work? Let's see. Let's say you have an array like the original array. Let's say it is 5 to 3 7. So this prefix array is a simple pre-computation. Let's take this. If let's say you don't pre-compute, okay, let's say you chose not to pre-compute, what would happen? You would take this array, and you used to take number of queries. What's the input format? So queries are given just after the array size. So let me take them q, and while q minus minus sorry, I will take int l, int r, and I would do this int sum equal to 0 for int I equal to 0, I less than, sorry, I equal to l, I less than or equal to r, I plus plus, sum plus equal to of I. Isn't it? This would just do my work, right? Wouldn't this do my work? Like I'm taking L and R and calculating the sum every time from L to R. It would work for sure. But it would give me a TLE because the complexity of this would be O of n into q. Isn't it? The complexity, the time complexity would be O of n into q. And if queries are huge and n is also huge, as seen in this problem, both of them are like 2 into 10 power 5. So n square won't work. N square won't work. Alright, n square won't work here. I need to find out some sort of a linear complexity. So there's a simple pre-computation known as a prefix sum. What it exactly does is, prefix of 5 is nothing. So prefix sum under this would be 0. Prefix of 2 is 5. So 5 would be here. Prefix of 3 is 5 and 2. The sum of 5 and 2 is 7. Prefix of 7 is 5, 2 and 3. 7 plus 3 is 10. Right? This 5 plus 2 is 7. 7 plus 3 is 10. And let us consider an imaginary element here. This particular element's prefix would be the whole array, whose sum is 17. So we are doing a simple pre-computation here, which would help us. We just need to make a prefix some array of size n, sorry, n plus 1, because we are also considering that imaginary element whose prefix is the whole array. So prefix sum of 0 would always be equal to 0 because the prefix of 0th element is nothing. And starting from 1, I less than or equal to then I plus plus. Prefix sum of I would be equal to the previous prefix would plus the current element. The previous prefix plus the current element. And with this, you have this prefix array. So can I say that if I consider the particular index R, let's say I'm considering some L to R, can I say that for every index I have the sum from 0 to that particular index, the sum from 0 to 1, 0 to like closed interval 0 to open interval 1 is in index 1, isn't it? 5 is in index 1 and 5 plus 2 is in index 2. 5 plus 2 plus 3 is in index, which index is this? 3, isn't it? So I have sum from 0 to R. I have sum from 0 to R for every index, isn't it? I have sum from 0 to R for every index. Where is this sum from 0 to R? It is in prefix of R plus 1. It's in prefix of R plus 1. Now, okay, so I can always get prefix of 0 to R and O of 1, right? I can always get prefix of 0 to R and O of 1. Is that clear? But I want prefix of L to R, like prefix sum of L to R. I mean sum from L to R. How can I do it? How can I do it? Let's say I want to find sum from L to R, this part, and I know sum from 0 to R. I know sum from 0 to R. If I remove the sum from 0 to L minus 1, if I remove the sum from 0 to L minus 1, can I get this particular sum? Can I get this particular sum? Isn't it? Can I get this particular sum? Right? From this, if I remove this, what else is remaining? This particular part, right? And this is what I want. This would be my desired sum. So this is what we are exactly doing. Okay. The formula is prefix of some index plus 1 is equal to sum from 0 to that particular index, and sum of L to R would be equal to sum of 0 to R minus sum of 0 to L minus 1, isn't it? Okay, so if I want to query for L and R, let me first convert L and R to zero based indexing by doing L minus minus and R minus minus. Now I want sum from L to R, so I just need to see out sum from 0 to R. What is it? Prefix sum of R plus 1 minus sum from 0 to L minus 1. What is it? Prefix sum of L minus 1 plus 1, which is nothing but prefix sum of L. Alright, so this would give me my answer. So that's how a simple prefix sum works. So let us create test case. Taking too much of time. Did we give a space here? Should we see next? Yeah, done. Is there any modulo thing here? No. Yeah, done. Accepted. So now let's move to the next question. Okay, so this says static range minimum query. And as we know, minimum operation is not associative. Why prefix sum only works for associative stuff? This is also important to know. First thing, while you're computing this particular thing, let's say 0 to r, and then you're removing whatever the result you get from 0 to l minus 1, right? That means to invert this particular thing, an inverse should exist. Like for sum, the inverse minus exists. Minus is an inverse, it exists. And sum is like, if you, even if the order changes, the sum would still remain the same. Due to this property, you can actually split the sum from 0 to r, sorry, 0 to l minus 1 and l to r. If it was not associative, this splitting was not possible. This splitting was not possible if the operation was not associative. And if inverse didn't exist, this particular thing won't be possible, the minus thing. So while doing prefix sum, always it should be associative and inverse should exist. But coming to minimum, is minimum invertible? Is minimum invertible? No. Is minimum associative? No. Minimum is neither invertible nor associative. Can I say minimum of this particular sequence and minimum of this particular sequence would share any kind of relation? Can I split them somehow? No, I cannot. I cannot split them. In these kind of cases, we use something known as a sparse table. So this thing is not very intuitive to implement. It is not very intuitive to implement. And I would suggest you to understand this logic very carefully. Then if you are clear with the logic, like if you are okay with the logic, if you understand it some 70%, add it to your template. Re-implementing all these stuff is a bit boring and it takes time. Okay, so it's similar to segment trees. It's something you would like to add in your template. So if I get started with this, but one thing, always be ready to implement these kind of stuff. Okay, it shouldn't be like someone takes away your template and you're really messed up. That shouldn't happen. That should never happen. Okay, so to get started, what is a sparse table? There are few contests in which templates are prohibited, like not the popular ones like ICPC and stuff, but there are few contests in which you can't actually use a template. Okay, so 5237. So if I want to make a sparse table for this, sparse table, the thing is very simple. Sparse table, let's say ST is a sparse table. ST of IJ would represent if you want to calculate the minimum, this would represent the minimum of range. Better I would type it. Okay, so ST of IJ would represent minimum of range starting from I of length 2 power j. Why 2 power j? We know that binaries are enough to represent all kind of numbers, right? So binaries are they can potentially represent all kind of numbers. So that's why to store some space and time, we use this kind of implementation. And if this is the thing, how would you query this? How would you query upon this? Querying even things is easy, isn't it? Querying even things is easy. Even lengths, I mean, even things in the sense even lengths. Querying even lengths is easy because, like, not even lengths. Querying 2 powers is easy. But let's say you have some other lengths which are not that easy. How would you break it down? Let's say you want to query 2, 3, 5 this way. Let's say you want to query 2, 3, 5. This is the case. So this is 0, 1, 2. This you can query easily, right? 2, 3, 5. You can basically write this as st of starting at 0, length is 2, this particular thing length is 2. So this would be, okay, if length is 2, 2 power what is equal to 2? 2 power what is equal to 2? 2 power 1 is equal to 2, right? So the minimum would be stored here. This would give you 2 answer. But let's say if you want to query 0 to 2, length is 3, right? But 3 is not a power of 2. How would you query it? So basically what you do is take minimum of this range, and come to a global minimum, like minimum of 2, 3 and minimum of 3, 5 and their minimum. Okay, so this would give you the minimum of this whole range, even if it's a not a power of 2, even if it's not a power of 2. Odd even doesn't matter. Sorry, my bad. Initially I was hallucinating a bit. It's not about odd and even, it's about powers of 2. Powers of 2 is easy to query, but if these kind of cases exist, this is how you would do it. Minimum of 2 and 3 and minimum of 3 and 5. Now let's talk about the actual thing, like how would you visualize it and how would you actually write code for it. Okay, so let us take what was the previous array which we took. Yeah, this one, right? 5, 2, 3, 7. Let's once again take the same array, 5, 2, 3, 7. All right. Now let's make the sparse table. Okay, sparse table would have indices 0, 1, 2. Okay, okay, there are 4 elements, so it would be 3. And here this thing would be, okay, let me add some more lines to it so that we can write freely actually. Okay, so here the index would be, let's take it 0. Okay, so let's take it 0 and tell me, can any particular range can have the length as 4? Yes, it can have 0 to 4, but can any range have the length 5? No, right? So maximum length it can go as 2 power 2. So this would at max go till 2. More than that, it's unnecessary. Okay, so let me chop it off and let me write it here. Okay, so yeah, what's the minimum of range starting from index 0 and of size 2 power 0, the number itself. What is the minimum of the range starting at 1 and length is equal to 2 power 0? 2 power 0 means 1, so the range starting at index 1 and of length 1 would be, there's only one number 2, and same for this. So if the length is 1, the number itself becomes the minimum. Is that clear? The number itself becomes the minimum. Is that clear? Now coming to the length 2 power 1. Okay, if some range starts at 5 whose length is 2, the minimum would be 2. If some range starts from 1 and length is 2, the minimum of 2 and 3 would be 2. If the range starts at 3 and length is 2, the minimum would be 3. If some range starts at 5 and goes till length 4, the minimum would be 2. Can any other start point take you to length 4? No. So let's keep it empty. There are no elements here. Fine. There are no elements here. And let's implement it here. Let's write a function to build this sparse table. So let's make a struct sparse table. Okay, int n, and this particular thing, let's call it the maximum log. Let's call it maximum log mxl, maximum log, and we would need a sparse table, vector of vector int st. And however, we would need these logarithms, right? We would need these logarithms. Okay, to decode the length, we would need these logarithms. So let's pre-compute the logarithms. Let's call it logs, or let's just simply call it L. Okay. The user would give you an array and you need to pre-compute stuff so that you would get a sparse table out of it. Fine. N would be array.size and max logarithm would be equal to 32 minus okay. This would basically give you this particular value. It's like the seal of log n base 2. It is seal of log n base 2. Sorry. It's the seal of log n base 2, and st dot assign n into max logarithm. That should be the size, right? Have a look at here. The size is n rows and max logarithm, whatever the size takes. Okay, that is the dimensions, and L dot assign n plus 1 comma 0. And let's set a separate build function. So if I want to build a sparse table, okay, so to this also we would pass our array fine, and first step will be pre-computing logarithms. And these logarithms are base 2, okay? They are not natural logs, they are log base 2. So L of I, logarithm of I equal to L of I by 2 plus 1. Okay. So we will build this level by level. Okay, we will build the sparse table level by level. What does level by level mean? First, let's say 0, 1, let's say it is 0, 1, 2, 3. I would first build this part 5, 2, 3, 7. I would build 5, 2, 3, 7. So let's build the level 0. Let's call it level 0. Okay, so sparse table of start point. These are the start points, okay? So if the start point is, let's say, some index, and the length of that particular range is 2 power 0, which is nothing but 1. That means only one element is in that range. So its minimum would be that one number itself, which is ARR of start. Okay, now let's build the remaining levels. Fine, let's build the remaining levels. So for int, okay, so level equal to, we have already built for level 0. Level would be less than max logarithm, that particular column size, sorry, row, what was it? Yeah, number of columns, and level plus plus, start equal to 0, start plus, okay, so start plus 2 power level, or should I name it length instead? Should I name it length or power something? Let's name it P. P for power. More intuitive. Okay, 2 power that particular. Okay, so this thing should be less than or equal to n, and start plus plus. Okay, start plus plus. So now for every start point we need to compute this. Okay, so if the sparse table has a particular start point and a length, okay, the power is equal to this thing. So tell me, if I want to compute it for level 1, what all things would come in level 1? One is 5 2 would come, and 2 3 would come, and what else would come? 5 2 2 3 and 3 7. Okay, these are all the things I need to compute, these minimums. That means 2 2 and 3. Okay, so that should happen. So that means if I'm standing here, I should be looking at this element, isn't it? I should be looking at this element and this element. So I should be looking at minimum of, okay, this particular start point and the previous length element. Okay, start point would remain the same and the previous length, so that particular start point would be included in it, and minimum of this and sparse tree of. One thing is clear, previous lengths are only computed, so I would go to the previous length only. Now I need to check for I plus 2 power, sorry, not I here. What was this? This was P minus 1, and start plus 2 power P minus 1. This is what I need to look for, isn't it? So this is what I should look for. I need to look for start and P minus 1 and start plus 2 power P minus 1 comma P minus 1. Why am I doing this? It could also be something like, okay, you came to P minus 1, you can check for the immediate next row, which is 1, which is fine in its own way, because 2 power P minus 1 is equal to 2 power 1 minus 1, which is indeed equal to 1. So always the next row would skip. Okay, the skipping would be the next row. But okay, fine, this would give you 2 2 3. But coming to index 2, you need to check for everything of length 4, isn't it? You need to check for everything of length 4. So if it's 5 2 3 7, you need to check for you have the length, you have everything for length 2s, right? So you need to check for the minimums of this particular ranges, isn't it? If you want to compute thing for length 4 out of 2, this is what all you should do, right? So now this should give you 2, and this just one skipping logic won't work. I need to check for, now I need to skip 2 places, now I need to skip 2 steps. Like, example is bad, please try to understand me, the example is bad. like there are only few elements, so I'm unable to explain. Let me take a bigger array. Let me take 5, 2, 3, 7, 4, 6, 2. Fine. Let's say this is the thing. Let's say this is the thing. Now let's say I need to check for four length elements. How would I do it? How would I do it? First thing, these things won't change. 5, 2, 3, 7, 4, 6, 2. This would be on the row 0. Now I need to check the previous element here and the previous element. Sorry, just skip one steps. One step. I would skip. This would give me 5 and 2. Minimum is 2. And 2 and 3. 2 and 3. Minimum is 2. 3 and 7. Minimum is 3. 7 and 4. 7 and 4. Minimum is 4. 4 and 6. Minimum is 4. 6 and 2. Minimum is 2. Isn't it? Isn't it? Now, the minimums of this particular ranges are calculated. Now I need to take 5, 2, 2, 3, 3, 7 to compute the minimum of 4 size elements. So what I would do, I would skip 2 steps. Now, okay, so the minimum starting from this particular 5, I need to find till 7, right? I need to find till 7. So the minimum would be the minimum of this particular thing, 5, 2, 5, 2's minimum, this particular thing here, sorry, this particular 2, and 2, 3's minimum, this particular 2, and 3, 7's minimum, this particular 3. Now I need to find these 3's minimum. Again, repeat the same process. Alright, so this would give me 2, and this would give me starting from 2, ending at 4, 2, 3, 7, 4, 6. This would give me 3. So every time I'm checking s plus 2p minus 1, comma p minus 1, isn't it? Previous computation, like previous column, and s plus 2p minus 1. And this would be equal to, in this case, p is equal to 2, right? 2p minus 1, so 2 power 2 minus 1, which is 2 power 1. So that's why I'm skipping 2 steps. I just need to compare the minimum of this range with minimum of this range. Isn't it? So I would compare this particular 2 with this particular 3, and I will get 2. 2 with 4, I will get 2. 3 with 4, I will get 3. 4 with 2, I will get 2, isn't it? So by this particular thing would reduce like this, in this fashion. In previous one also we saw the same. So this would reduce this way. So what's the formula for this? Start plus 2p minus 1, p minus 1. Is that clear? The building logic is clear. I hope. Now, coming to the query part. If I want to query this range. Okay, if I want to query this range with L and R. Okay, L, let's take capital L because logarithms you already took L, that pre-computation array. So now I need to find length, which is equal to R minus and power would be equal to log of length. Okay, log of length, isn't it? To get the power, log of length. And how would I query this? Okay, so I need to return minimum of sparse table of start point is L, and the length I would go till is 2 power p. So the power would be equal to p. Or it could also be at r minus 2 power p plus 1. Sorry, not plus 1, plus 1 and j. Okay, so the length is fixed, and this would give you the nearest 2 power, isn't it, from right end. So how would this querying work? How would this querying work? Okay, so let's quickly do it for the previous array which we took. 5237, 5237, 223, and 2. 0, 1, 2, 3, 0, 1, 2. Okay, so this would be the sparse table for 5237. If I want to query the minimum, if I want to query the minimum of, let's say, this is 5237, right? Let's say I want to query the minimum of this particular range, 5 and 3. So I want to query the minimum of 0 to 2. Okay, so my length would be equal to 3. My length would be equal to 3. And if I take 2 power for this, it would give me 1. It would give me 1, isn't it? Isn't it? What's log of 3? Log of 3 is equal to log of 3 by 2 plus 1, which is log of 1 plus 1. And log of 1 is 0. Log of 1 is 0. So this would give me log of 1 plus 1, which is equal to 1. Now, coming to this thing, what I would do, I got the p, the power. Now, st of L is 0 and my p is 2. Sorry, my p 1. P is equal to 1. Okay, and this particular thing, st of 2 minus 2 power 1 plus 1. So this is basically st of 1 1. So this would give you 0 0 1 and 1 1. Okay, so start this particular, what is st of 0 1? st of 0 1 is starting at 0 of length 2, and this particular thing is starting at 1 of length 2, isn't it? That's what I told you earlier exactly. If you want to query this kind of stuff, if you want to query this whole thing, you would consider this thing and this thing and their global minimum. Their global minimum would give you the answer, isn't it? So that's what we are doing here exactly. So I hope the build logic and the query logic is clear. Alright, so this is how you build a sparse table. This is how you build a sparse table. Fine. Now how can we actually use it? The question says you'll be given A and B, one based indexing. So first step, IO is based sync with SDD of false and seen by null pointer. Okay, so some CSCS problems doesn't pass without fast IO. Are we given any sort of test cases? No, directly the array itself. Okay, wait, queries, right? Converting them to zero based indexing, and we would need a sparse table. So let's create one sparse table st, and let's pass array into it, just the constructor, just the way constructor demands, and sparse table would be built. Okay, sparse table would be built. Now I would do st dot query lr, and this would be my answer. Okay, so let's create this. J was not declared. Okay, in my original template, let me be very honest, I'm habituated to writing this as ing. We forgot a semicolon here and somewhere we wrote J, it seems. So this should be power instead. Did we miss something? Did we miss something? This is a void function. Where did we miss? This thing, okay. I often do this mistake, that's why it was easy to recognize. Yeah, and this passed. So let's try to submit this. I've done some very standard mistakes so many times such that it's easy for me to find out my mistakes. Okay, so this got accepted. So that's how you implement a sparse table. You can use this data structure for things like minimum, maximum, GCD, etc., which are not associative and invertible. Alright, and it's more optimal than segment trees. You can do the same problem with segment trees also, but it's always better to use segment trees, which we'll discuss in the next video, the exact next video. Segment trees should be used only when there's some sort of updation, like if it's some sort of dynamic thing. The range queries are dynamic, then only use segment trees, otherwise use sparse tables and prefix sums. Okay, so the whole computation this thing would take n log n, and querying would take O of 1. Building would take n log n and querying would take O of 1. So this is much more optimal than seg trees. So that's it for today. I hope uh, the lecture was interesting. And suggest me some more topics, guys, so that I can cover more stuff. I honestly don't know what kind of doubts do people actually have. Okay, so thank you everyone.